This is the ninth video of the series Business Forecasting, and we were discussing time series analysis. In the last video, that is video number 8, we discussed simple linear regression, but in that video we discussed only the theoretical part of the method. And so in this video we are continuing that topic only, that means simple linear regression, but in this video we'll try to see how to implement that using an SPSS software package, and after implementation we will try to interpret the report, that is the regression output and the graphical output also, in the best way possible. So let us start now. So this is a time series data. This is now in Excel sheet. So I will copy this data. This is you can see here, this is the period number that is running from 1 to 33. That is, there are 33 periods for which the sales figures are noted. And so I will copy this from here and paste this in my SPSS worksheet. So in SPSS you have two type of worksheet. One is the data view, that means here it is like Excel, you have to paste the data simply. So take it from here, don't copy the headings, so only the numbers that need to be copied. So copy it from here and then paste it here directly. So once you paste it here, you need to go to the variable view and need to change the name. So the first variable is period and the second variable is sales. And for the period, the decimal point should not be 2. See, it is an integer value, that is 1 2 3 4, like that. So 1.00, 2.00, it is not a very good way to represent it. So let us keep it 0 decimal, and for sales it is okay, it is 2 decimal. And only thing that need to be changed here is the measure, that is both this measure should be scale. So make sure that these are selected scale here. So once this is done, the data part is complete. So go to analyze and then regression and then linear regression. So click here, this is the option. So first of all you have to enter the dependent variable. Note that the dependent variable is always sales. So click here, and for independent variable, the independent variable is time, that is the period. So enter here. So once this is done, you go to statistic, and you don't have to change anything here. For simple linear regression, keep it as it is. In plots, you make sure that you select this option SRE SID. This is the standardized residual. So enter it in Y and then dependent variable in X. So your SRE SID should be in Y variable, and this dependent is your X variable. So basically what it will do is, it will develop a scatter plot where the in X axis it will have the dependent variable, that is the sales, and in Y axis it will have the standardized residual. So what is standardized residual, we will discuss later on. And then you check here also normal probability plot and continue, and then you need not change any other parameters here, just click on OK. So once you click OK, the report will be generated like this. So you can see this is the report, and the charts will be also generated. Now if you check any regression output, either you can use any software like SPSS, it is here, but you can use Excel also, or Minitab or R or any other software. The basic output will have 3 portions. So the first portion is model summary, the second portion is ANOVA, and the third portion is coefficients. So let us go to the slides and discuss each of these portions, each of these parts one by one. What does this signify? So I'm going to the slides now. So first of all we will discuss the regression equation, that means we will focus on the coefficients parts of the regression output. So in your coefficient part, you can see here the constant is given and period is given, and so your period is that independent variable, and the coefficient next to period, that is 0.13, this is the slope coefficient, that is b1, and the coefficient next to the constant is 9.007, so this is your intercept. So your regression equation should look like this. So this is your dependent variable forecast, that is y prime, and this is your intercept, that is b0, and finally this is your slope, that is b1. So your slope here is 0.130, and the intercept is 9.007, and this is your forecast variable, that is your dependent variable. And in case of time series analysis, you can define this as t. So since we are discussing time series analysis, so instead of writing the independent variable x, you can write it t, or you can use x also, that is not a big problem. Okay, so this is your first job, that is the identifying the coefficients of the model. Next is the ANOVA. So remember there are three parts. One is the coefficient part, the next one is the ANOVA part, and the third one is the summary output. So let us now discuss about the ANOVA part. But before doing that, let us have some idea about what is an ANOVA. So an ANOVA is a special kind of hypothesis test where the test is done for checking the groups, whether the groups are coming from a single population. So for example, I have given you an example here, that is group 1, group 2 and group 3. There are three groups. In the group 1 there are observations like x1, x2, x3 and so on. Group 2 has observations such as y1, y2, y3, and group 3 has z1, z2, z3. So these are observations of any measures, like for example weight or height or anything, any variable that is being measured. So in case of ANOVA, there are two types of variabilities that are discussed. The first one is the within group variability. That means the variability within a group. That means the variability of, suppose in group 1, between the x values, that is x1 variability between x1, x2, x3. Then in group 2, variability between y1, y2, y3, and then in group 3, z1, z2, z3. So once these variabilities are found and then you add this gives us the within group variability, this one. And then there is another type of variability which is called the between group variability. So for example, if you check the variability between x1, y1 and z1, then between x2, y2 and z2, and then sum it up, add them, that will give you the between group variability. So these two types of variability are there. So then in ANOVA, they will calculate the mean square error. So mean square of treatment and mean square of error. So what is the mean square of treatment? That is the between sum of square, that is this value, divided by the degrees of freedom of treatment, and the within sum of square, that means this value, and divided by degrees of freedom of the errors. How to calculate the degrees of freedom, that we will discuss at some later point of time, but uh, just by looking at the report. But in this way, these two mean squares are calculated, and this ratio is being calculated. Now see, if this between group of errors, between group variability, if this is substantially more than this within group variability, then we can say what? We can say that there exists certain kind of differences between these groups. So the between group variability is more than, significantly more than the within group variability. That means these three groups are from little bit different from each other. But suppose the between group variability and the within group variability are not much different, that means they are almost equal to each other. So that means we will say that although these are written in this way, that is group 1, group 2 and group 3, they are basically coming from single population. That means you can write x1, x2, x3, then y1, y2, y3 in single column, and that will be one group only, one group. where only some within group variability exists and the between group variability is not significant. So therefore there can be two types of situations. So the between group variability is not significantly larger than the within group variability. In that case, our conclusion will be that the groups from the single population, that is the population is the same and there is no such differences between these three groups. And situation 2 is between group variability is actually significantly larger than the within group variability. That means these groups are not I mean same, they do not come from the same population and they are different from each other. So this is how normal ANOVA is designed and implemented. But we are not discussing normal ANOVA, we are discussing regression. So how this can be implemented in case of regression? Let us understand. If you have seen the previous video, that is video number 8 from the last lecture, so you have gone through this particular diagram, and if you have not, so please go back to that video and watch it again and then come back here. So in this diagram we were discussing that um, this is the y value, that is the dependent variable axis, and this is the x value, that is the independent variable axis. And for each value of x, like x is equal to 1000 and x is equal to 2000, we will have a particular distribution of the values of x like this one, and the mean of that distribution is your mu y, and that mu y will pass through a certain straight line which is given by this equation, and this is the population regression equation of mu y with respect to x. This was the discussion done in the last lecture. And if you just try to interpret the beta 1 and beta 2, this is the slope and this is the intercept. How is this slope defined? This slope is defined as if the change in independent variable is 1 unity, then the change in dependent variable, that is mu y, the magnitude of change is given by the slope, that is beta 1, and this is the intercept value, that is the value of mu 0 mu y when x is equal to 0. So that is beta 0 value is the intercept of the population regression equation. So okay, so now let us extend the theory of ANOVA into the context of regression. So in this case, the within group variability is in this direction. That means by group here we will mean the distribution. The distribution itself is the group. So within that group, the whatever variability is there is your within group variability. And what is the between group variability? This is in this direction. That means the variability between these two groups or these two distributions. So this is one group, this is another group. So between these two groups, the distribution is known, the variability is the between group variability. And in the similar manner, the reports the MST value and MSE value will be calculated. That means the between sum of square divided by the degrees of freedom of the treatment and the within sum of square divided by the degrees of freedom of the error. So what is this error? Error is the residual. We have already seen error is the residual. And treatment, what is the treatment? In our case, the treatment is the regression. So regression is treatment and residuals are the errors. And the report will give you these values, that is MST value and MSE value, and by dividing that it will give you an F value also, and that F value has to be compared with the critical value of the F distribution, and based on that, if that is less than your F critical value, then we will say that the conclusion is that insignificant between group variability. That means the between group variability is not significantly larger than the within group variability, and therefore the F value, that is this ratio, this is the F value. If this is greater than your critical value, then we will say that there is a significant between group variability. So now try to understand the logic here. If there is significant between group variability, Then from where that variability is coming? In the last lecture, I have already discussed that between these two groups, that means these two distribution, only one thing is different. What is different? Only this mu y is different. The sigma value, that is the variability variance or the uh, variance or the standard deviation, these things are equal among these distributions. So the only difference that is occurring, that is happening here, is due to this mu y values. If these mu y values are equal, then these distributions will also be equal. So now if you are saying that there is a significant between group variability, that means that kind of difference is only coming through your mu y value, and your mu y value can only have some difference from x to x when your beta 1 is significant. That means if your beta 1 is not equal to 0, then only you can say that the mu y values are different from this distribution, for these distributions. Otherwise, for beta 1 is equal to 0, the mu y also will be equal to beta 0, and therefore equal for all these distribution. So you have significant between group variability, that itself signifies that the difference is coming from mu y, and therefore the beta 1 value is not equal to 0. So try to reflect on this. The ANOVA is indirectly showing you that, first of all, it is directly showing you that there is a significant between group variability, and we have seen here that the group means distributions here. So if there is a between group variability which is significant, that significant variability is coming only through mu y, because the sigma is equal anyway, and mu y can only be equal different only if the beta 1 value is not equal to 0. So therefore a significant ANOVA gives rise to a conclusion that beta 1 is not equal to 0, which means what? Which means that you have a linear equation, you have a positive slope or negative slope, but non-zero slope. That means the linearity or the linear assumption is true in this case. Or in other words, the model you have chosen, that is a linear regression model or a linear model, is significant overall. So this is about the ANOVA. Now let us come to the report that was taken out from the SPSS output. So this was the ANOVA report. You see, these are the two sum of square values that we will get. This is the regression sum of square, and this is the residual sum of square. So basically this is the SST. SST is your 50.919, and SSE, that is your 7.193. Now they have calculated MST and MSE. What is MST? This is the MST and this is your MSE. So MST is 50.919, and what is MSE? MSE is 0.232. How this has been calculated? They have divided SST by degrees of freedom of treatment. And what is the degrees of freedom of treatment? This one. This is always equal to your number of independent variable. How many independent variables you have here? Only one. That is the predictor. That is the period, basically T. The period, only one independent variable is there, and therefore the degrees of freedom of treatment will be always equal to 1. And the total degrees of freedom is n minus 1. N minus 1 degrees of freedom of total, that is n minus 1. What is n? N is your total number of samples. In this case this was 33, so this is 33 minus 1, that is 32. See, 32 here. And since this is the total, you subtract this one from this one to get this one. So the degrees of freedom of residual is equal to degrees of freedom total minus degrees of freedom treatment. That is, in this case, how much? 32 minus 1, that is equal to 31. This is your 31. And how they have calculated MST and MSE? They have just simply divided SST by degrees of freedom of treatment. That is your 50.919 divided by 1. That is 50.919. This is MST. And what is MSE? MSE or degrees sum of square of errors divided by degrees of freedom of errors. That is residuals. That is 7.193. That means this one, and divided by 31. If you do this, it will be 0.232, which is written here. Now once this is done, they have calculated F statistics. How this is calculated? This is the division, that is MST by MSC. That means 50.919 divided by 0.232. If you do this, 219.436, this will come. So this is your F statistics. F statistic, that is calculated, and this is greater than your F critical value. How do you know that? You know that because your significance value is less than 0.05. If your significance value, that is the p value of the test, this is less than 0.05, that is your chosen significance level alpha is equal to 0.05. If your significance value here is less than that, that means your F statistic value is greater than your critical value of the F distribution. And if that occurs, you know what is the conclusion. We discussed it already. The conclusion is that your between group variability is more than, significantly more than your within group variability, and therefore, as we discussed before, your beta 1 value, that is this value, is significantly different from 0. In other words, the linear regression model that you have chosen here is significant overall. So this becomes your null hypothesis, beta 1 is equal to 0, and this is your alternative hypothesis, beta 1 is not equal to 0, and using this you reject this null hypothesis. So your null hypothesis is rejected, and therefore your beta 1 is not equal to 0, and your model is overall significant. So this was all about the ANOVA. Now let us come to the another part of the story, which is the R square and standard error. In the last lecture we have seen this diagram, that is, this is the regression line, the center line here, this is your regression trend line forecasted using the regression equation, and these are the actual points, actual sales say, and this is the forecast, and these are the error values. This we have seen already, and this was the calculation for errors, that is the y1 minus the expected y1, that is the expected value of y using the regression equation. So actual value, this was the actual value, and this is the forecast. So actual minus forecast will give you the error in this way. So now come to the definition of the standard errors. The standard error of estimates, that is calculated in this way. That means the error squares, sum of the error squares divided by n minus 2, n is your sample size, the entire ratio, and the square root of that. That will give you the standard error of the estimate, and in this way it is calculated. And then there is another standard deviation, which is the standard deviation of the y variable. This has got nothing to do with the regression. This is just the sample standard deviation of your y variable. So you have y1, y2, y3, y4, in this way many values of the variable y here. So you just taking the standard deviation of this range. So that value is this one. Okay, so now your R square is calculated in this way, that is 1 minus SSE by SY whole square of that. So in this way the R square values are calculated and the standard error is also calculated. So if you look at the regression output, they have given you the R square value here, that is your 0.876. So now let us look at the R square value and the calculation once again. So this was the calculation. Now what is SE? Is as per the formula given in the previous slide. This is the variability due to the errors only, as we have written the formula. What was the formula? SSE was equal to square root of summation et whole square divided by n minus 2. So this variability is coming only from the errors. So this is the numerator is the variability due to the errors. And what is SY? SY, I told you that it is the standard deviation of only the Y variable. That means it is a total variability. It has got nothing to do with the regression. So it is a total variability of the Y variable. So if you just arrange this in a different way, that means in the numerator, the total variability minus the error variability divided by total variability. So if you subtract the error variability from the total variability, that gives you the variability due to treatment or regression. So therefore, the interpretation of R square is the ratio of variability due to treatment by the total variability. That means the percentage of total variation that can be explained by the model. So the numerator is the explained part and this is the unexplained or the error part. So the R square value gives you the variability of the treatment part, that means the regression part. So if your R square value is 0.876, that means this is completely wrong. This should be 87.6. 87.6% of the total variation is explained by your model, which is a very good indication for the explanatory power of the model. This is called the explanatory power of the model. So in any model, the R square value you should target to it should be like at least 70%. Anything below 70% is not very good fit for the model, and if it is more than 85% or 90%, then it is considered very good, like in this case. In this case the R square value is 87.6%, which is considered a very good explanatory power, because 87% of the total variation of Y is explained by the model. Only like 13% is unexplained. And what is this R value? R value is obviously the square root of R square, and if you do that, that means the square root of 0.876, this will give you 0.936 as it is written here. And interestingly, this is your correlation coefficient. So if you calculate the correlation coefficient, which one? This is the Pearson correlation coefficient is your R value, that is 0.936 here. So if you have studied correlation, you know that any correlation value that is greater than 0.5 is considered a moderately strong correlation, and if it is like 0.9 or 0.85 or anything like that, that means there is a very strong positive correlation between the two variables. So that also indicates a good fit. However, the correlation does not indicate any causality. For that, regression analysis is required. Anyway, that we will discuss in some other point of in time in our causality models. Anyway, so here we discussed the standard error and the R square value. So it is better to focus always on R square value, because you cannot pinpoint anything on standard error. So if you say that my standard error is 0.481, so what does that mean? Is it less or is it more? So whether should we accept it or we reject it? We don't know because we don't have any benchmark. Benchmark is only applicable. That means you can say only SSC, that is the standard error, is good or bad, less or large, based on the value of your total variability, that is SY. If that is known to you, then you can only say it is standard error is compared to SY, it is large or it is less, something like that. But you don't have to do these things because you have the R square value which already takes care of this ratio. So always focus on the R square value. Okay, finally, the significance of the individually independent variables. So this is not really so important for a simple linear regression, which where you have only one dependent variable. Basically, what they are testing here is, again they are testing beta I value is equal to 0 versus not equal to 0. So if multiple variables, independent variables are there, so multiple such hypotheses will be there, like beta 1 is equal to 0, beta 1 not equal to 0, then beta 2 equal to 0 versus beta 2 not equal to 0, and so on. But in case of simple linear regression, you have only one variable, that is beta 1 basically. So this hypothesis is will be in exact match with the ANOVA hypothesis in case of simple linear regression, and therefore if you take out the ANOVA report, this significance value and this significance value, this will be always in perfect match in case of simple linear regression. So therefore the coefficient part of the report should always be considered only to identify the slope and intercept that we have discussed already, and for the t-test, that is the independent sample t-test, for the individual coefficient you can ignore it for the time being when the model is a simple linear regression having just one independent variable. So that is all about the discussion part or the interpretation part as far as the report is concerned. So let us move to the SPSS report once again. So as you can see here, this was the report. Now we will interpret the charts. So you can see here we have taken out two charts. The first chart, this is called the normal probability plot. Normally in some other softwares like Minitab or R, they will give you the p-value also. So in that p-value, if the p-value is greater than 0.05, then you will say that the data is normal, otherwise not normal. In case of SPSS, such reports are not available somehow, at least in this report. So we will just make our conclusion by looking at the graph. You should always look at the graph like in this way. The points here, these scatter plots, this should follow the straight line mostly, which is occurring here. That means if you can check here, these points are almost lying on this line, on the straight line. If that happens, that means that your residual values are actually normally distributed. This should be one checkpoint. Another checkpoint is coming from the scatter plot of standard residual with respect to the dependent variable. The checkpoint here is, if you have a zero line here, you have this zero line, you can see here, the number of points above the zero line and the number of points below the zero line should be equal. Not exactly equal maybe, but almost equal. That means the share of the points above and below the zero line should be matching. Here you can see also, if you consider this zero line, the number of points falling below the zero line and above the zero line are almost equal. So therefore the model is not too biased, we can say. So these two checks are required here. So always implement these two plots also. You can implement this using Excel also, but I am using SPSS, so I did this. But in Excel you cannot implement this normal QQ plot or PP plot. So that was it in your so that was it. Let us go to the slide once again. So pretty much that was the interpretation and implementation of the simple linear regression model. So in this last slide I have just made a summary of the list of the checkpoints that you need to interpret when you take out a regression output. So there are 7 points that you can see here. The first column is for the checkpoints. What are the checkpoints? Next column is for the guideline, that is what is to be checked. And the third column is in this context, that means for this particular problem that we have taken in this video, what are the observations. So for example, the first point is the slope and intercept that we will note from the coefficient section, and in this particular case the coefficients are intercept is equal to 9.007 and slope is equal to 0.13. So this is the first observation. Second observation is the significance of the slope. Third is ANOVA. All these things I have already explained, so this is only a summary of the tasks that you need to perform. So if you just like, you can copy it, take a screenshot of this slide and use it for your future reference. So that is all about the implementation and interpretation of simple linear regression. Let us meet in the next video. Until then, goodbye and thanks for watching this video.